Hey everybody. Today we're talking about enumeration, which just means counting the number of elements in a set. When you're studying probability, this comes up all the time. In particular, if you have a finite sample space and all of the outcomes are equally likely, we often make the probability assignment that the probability of an event is just the number of outcomes in the event divided by the number of outcomes in the sample space. So to compute that classical probability, you need to enumerate both E and S. The most important tool that we use when we're enumerating sets is the fundamental counting principle. Basically, this says that if you have two events and the first one can occur in m ways and the second one can occur in n ways, then the two events together can occur in m times n ways. Sometimes this gets called the multiplication rule for enumeration. Simple example, a menu includes 4 soups and 3 salads, so there are 4 times 3 or 12 possible soup and salad combinations. And we can visualize that with a tree diagram. So here you can imagine the first branch at the top of the tree is where we choose our soup. There are 4 possibilities. And then regardless of which soup we choose, we then have 3 possible salads to choose from. So that's the lower branch on the tree. At the bottom, you can see you have 12 nodes. There are 12 total combinations for soup and salads here. The fundamental counting principle only applies when the number of ways that the second event can occur is independent of the outcome of the first event. For instance, if we're at that restaurant and we only like one of the salads if it goes with a particular soup, we can no longer use the multiplication rule, the fundamental counting principle, in the same way, because the number of salads that we have available to us is different depending on which soup we choose. In fact, the actual number of combinations is 3 times 3 plus 1. 3 salads that go with 3 soups, and then 1 more salad that only goes with one particular soup. The fundamental counting principle can be extended to arbitrarily long sequences of events. So for instance, if that same restaurant has 4 salads, 3 soups, 11 entrees, and 3 desserts, then the total number of meals possible is 4 times 3 times 11 times 3, or 396. Here's another example. How many different ways can a group of 4 people stand in line? So I recommend pausing the video, trying this one on your own before proceeding. So going from the front of the line back, there are 4 ways of choosing who's in front. And then regardless of who stands in front, there are 3 ways of choosing the second person, and then 2 ways for the third, 1 for the fourth. So by the fundamental counting principle, there are 4 times 3 times 2 times 1, or 24 ways that the 4 people can be arranged in this line. This comes up so often that it has its own name. If we're taking the product of the first n integers, that's n factorial, it's written n exclamation point. So for instance, 5 factorial is 1 times 2 times 3 times 4 times 5, or 120. Factorials get big very, very fast. Even just 10 factorial is already well over 3.5 million. This next example is going to lead us into our next topic. 12 horses enter a race. How many ways can they win, place, and show? So there are 12 ways that the first horse can be chosen, 11 for the second, and then 10 for the third. By the fundamental counting principle, the total number of ways that those 3 positions can be filled is 12 times 11 times 10, or 1320. This can be generalized. Suppose we have n items and we want to arrange k of them, where here we're assuming k is no bigger than n. We can do exactly what we did in this example. N times n minus 1 times n minus 2, multiplying by every integer, going down by ones, until we have k total things that we're multiplying. This comes up often enough where it has its own name. We read this as n permute k. A more succinct way to write this using factorials is that n permute k is n factorial over n minus k factorial. And the reason that this works is that all the factors in the denominator have matches in the numerator. If you write everything out and you start canceling things, you just are left with the original formula, n times n minus 1 times n minus 2, etc., until you're multiplying k things. Here's another example for permutations. A collector owns 53 figurines and wishes to arrange 8 of them on a display shelf. The number of ways they can do it is 53 permute 8, which is 53 factorial divided by 45 factorial. And that is nearly 36 trillion. So permutations get big pretty fast as well. Permutations count the number of ways that k things can be picked in order from a collection of size n. But sometimes when you're picking k things from a collection of n, you don't care about order. You're just thinking how many groups are possible. Those are called combinations. We abbreviate it n choose k, and the formula is n factorial over n minus k factorial times k factorial. The formulas are very, very similar for npk and n choose k. If you look at those, the only difference between them is that n choose k has another factor of k factorial in the denominator. Permutations are counting possibilities when order matters. Combinations count possibilities when order does not matter. It makes sense that there would be more possible permutations of size k from a set of size n because you have more choices to make, not just the items that you pick, but also what order they go in. If you take those two formulas from the last slide for npk and n choose k, you can relate them just by noticing that npk is n choose k times k factorial. And this has a very natural interpretation. If you're counting permutations, you count the number of ways you can choose the k objects. There's n choose k of those. And then you count the number of ways that the k that you've chosen can be put in order, k factorial. And so to get the total number of permutations possible, you apply the fundamental counting principle, n choose k times k factorial. The notation n choose k can be awkward when you're writing equations or doing algebra, and in a probability course, you need to do both of those things. So frequently, we end up using this alternative notation. We write n choose k with these parentheses with then n over k, and you can still read that as n choose k. We also often use the phrase binomial coefficients to refer to the numbers n choose k. And the reason is that if you take a plus b to the n and you expand it out, then the coefficient of a to the n minus k times b to the k is exactly n choose k. Here's a solved example. 3 of the 12 horses in a race are randomly selected for drug testing. The number of ways the horses can be chosen is 12 choose 3. It doesn't matter what order these horses are chosen, it just matters which ones we choose. Here's one for you to try. How many ways can a committee of 4 people be formed from a class of 20 students? So in this case, order does not matter. So we're going to compute combinations 20 choose 4. That's 20 factorial over 16 factorial times 4 factorial, just a little bit less than 5,000. Related example. How many ways can a committee of 4 people be formed from a class of 20 students if the committee must include a president, vice president, secretary, and treasurer? So this time order does matter. So we're talking about permutations. We're going to do 20 permute 4, 20 factorial over 16 factorial. We get 116,280. Again, remember, permutations count the number of ways that k things can be chosen out of n possibilities when order does matter, whereas combinations are selecting k things from a total of n when order does not matter. One final example. How many ways can a committee of 4 people be formed from a class of 20 students if one person has to be designated president? So in this case, we're going to need 2 steps, including the fundamental counting principle. First, we pick the president. There are 20 ways we can do that. We pick any one of the 20 students. And then we have to choose the remaining 3 members. And when we choose those remaining 3 members, order does not matter. There are 19 students left because we've already appointed the president. We need to pick 3 of them. Overall, there's 19 choose 3 ways that we can do that. So the total number of ways we can form the committee under these circumstances is 20 times 19 choose 3, 19,380.